Hey everyone, what's going on? Adam the Tutor here, coming at you with, well, the rest of Part D of this whole guy. So, let's just jump straight into it, right? So, our next G of T was case 2, right? And I'm going to underline that in this green color, right? This is our case 2, right? So, then, if that is our case 2, we're going to have then, okay, so let me do 2. So then our x sub p sub t is going to be equal to the integral from 0 to t mu of t minus t prime exponential minus gamma over 2 t minus t prime sine of gamma t minus t prime over gamma, and then we're going to have a c and a mu t prime minus t sub d, and then a cosine omega t prime minus t sub d dt prime. Okay, so you're looking at this and there's like 5 different functions, right? So you're like, I don't even know where to start. Well, let's start with the unit step functions, right? Okay, so first of all, let me just outline our region, right? Our region is going to be t prime is less than t but greater than 0, right? That's our region that we have. Okay, so this first one, which I'll underline in red. Okay, this first one, what does this one say? Well, this one is basically saying that until t prime is greater than t sub d, then our particular solution will be 0, right? Because if you'll recall, the unit step function, if we have mu of t minus a, this is equal to 1 for t greater than or equal to a, or 0 if t is less than a, right? That's how the unit step function behaves. So basically, t prime has to be greater than t sub d, right? So basically what that means then is that first unit step function changes the boundaries of integration to be t sub d, and then we can include an equals here now, right? So that's our new boundary. So how does that affect our integral? Well, the bottom limit will change to be t sub d, right? And then, so now that this is true, this guy is just 1, okay? Now, what about this one, which I'll deal with in the dark blue? Okay, so this guy right here, what about him? Well, again, that's saying that t has to be greater than t prime. Well, as we can see, t is always greater than t prime, the way our region is set up. So basically what that means is, by the same argument that we just made over here for the unit step function underlined in red, this guy is just going to be 1, right? So we've already knocked out 2 of the 5 functions that we need. Okay, so unfortunately, the next part is not so quick, and I'm not going to go through the whole thing in this video, because it really is a lot of just kind of painful algebra. Hey, I'll be honest, it does get a little monotonous, but I did it, and I got the following answer. Okay, so get ready, because this is a long one, right? We have have that our particular solution is equal to, and I'm going to make a quick definition here. I'm going to let omega squared be equal to gamma squared over 4, and omega is going to be equal to negative gamma over 2, right? So that's what I'm working with here. Okay. So, with that definition, I get that the particular solution is going to be C, and then minus omega, and then we're going to have omega squared, and then plus omega minus gamma squared, and then that's going to be times 1/2. Then we're going to have sine omega t minus t sub d. Should probably call this tau or something, maybe, because I'm going to be writing it a lot. Oh well, it's fine. T minus t sub d sine gamma t minus t sub d, and then we're going to have for our next one, let me scooch my chair up here so I can get in on this, we're going to have plus a negative big omega, and then that's going to be omega squared plus little omega plus big gamma squared times 1/2, and then we're going to have minus sine, and then that's going to be little omega t minus t sub d, and then we're going to have minus the exponential t minus t sub d, and then I believe there should be another sine, yep, sine gamma t minus t sub d. And now we got to start a second line, and then we're going to have plus, oh, whoops, sorry. I called it something else when I worked it out, so having to translate between that. So then that will be omega minus gamma, and we're going to have big omega squared, and then plus little omega minus gamma squared. We're also going to have a times 1/2 here. And this one will be minus cosine omega t minus t sub d. And then we'll have a plus exponential, right? And then we'll have a cosine gamma t minus t sub d, and then we'll have plus omega plus gamma, and then so I imagine this is going to be big omega, little omega plus gamma squared times 1/2. And that's going to be cosine omega t minus t sub d minus exponential t minus t sub d cosine gamma t minus t sub d, and then we come here, and then finally we have that. So that is our particular solution, and wow, that took a long time to write. Okay. So, now, we have the second solution for our case number 2. And remember what I said. Now, going into case number 3, what did I say about case number 3? Well, it's basically case number 2 with omega equal to 0, right? So, basically, what we can do then is we can rewrite case 3. See, so basically what we'll get is everything. So, this guy will be 0. Okay, so let's see here. I'm trying to decide if I want to write it out or not. Because, well, I guess I could. It wouldn't be too horrible. Okay. So, for this case, we have that it's C, and then we have negative omega, and we have omega squared plus big gamma squared times 1/2. This one will be 0. We'll have minus exponential t minus t sub d, and we'll have sine gamma t minus t sub d, and then we'll have plus negative, and then omega squared gamma squared times 1/2. We'll still have a 0. Oh, and I meant to put a thing right here. We'll still have a 0 there. So this will still be minus e, and then t minus t sub d, and then sine gamma t minus t sub d, right? And then, boom, right there. And then, okay, so now we'll have a plus, and then minus gamma omega squared plus gamma squared times 1/2, and we'll have a minus 1 plus exponential, right? And then we'll have a cosine gamma t minus t sub d, and then we'll have a plus and gamma omega squared gamma squared 1/2. Then we'll have a 1 minus exponential t minus t sub d. We're almost there. Cosine gamma t minus t sub d. And there's all that. Okay, so now just to kind of recap what's going on. Okay, just basically from a physical standpoint. Okay, so in this first case, the one underlined in the light blue, what's going on is that we start off with our the name escapes me, complementary solution. Right, it decays to half of its amplitude. This the time that we found in part C. It decays, its maximum amplitude decays to half of its original value. Then we kick it with this really quick pulse. Like it's almost like if you were to just jerk it really quick, right? You grab the mass and you just pull it really quickly, right? And then let it go. And so basically what happens then is we get a particular solution that it'll die off after after a long time, which is what we'd expect, right? If you don't have a sustained force, eventually after a long time, no matter what intermittent quick force or quick pulse of a force you apply to it, it's, eventually it's going to come to rest, right? So that makes sense, right? And that's exactly what this first particular solution is saying, right? In the second case, we have this really complex this really complex, combination of sines and cosines, right? Now, eventually, after a long time, remember, because this omega right here is negative. So all these little exponentials that are in it, maybe I should do this in green because that was our original color for this, right? All these little exponentials are gonna go to zero after a long time, right? So eventually we're just gonna be left with sinusoidal behavior, but it's gonna be with frequency omega, right? If you look at that, all the decaying exponential terms are on the gamma, not the omega, or the little omega, right? So basically what that's saying is that eventually this oscillator is going to take on the characteristic of the forcing function that's sinusoidal in nature, which makes sense, right? If the original oscillator is dampened, eventually that's going to decay to zero. But if you have this sort of background oscillation going on, eventually, that's being forced. Maybe there's some machine that's pulling the spring through the viscous fluid. Eventually it's going to take on that frequency. So that also makes sense as well. And then finally, we have this situation where, okay, so, and I didn't really have a color picked out for this, so let's do pink. We haven't done pink, right? So if you'll notice here, the exponentials are still on the sinusoidal terms, right? But now what you have going on is eventually this will settle to some equilibrium position. And actually, I think we could simplify this a little bit more, a little bit better. So that's a minus, that's a minus, that's a minus, that's a minus, so that's plus, right? And, well, actually, eventually this will go to zero. So let's take the limit. So limit as t goes to infinity, right? So this guy goes to zero, this guy goes to zero, this guy goes to zero, and this guy goes to zero. So what we're left with is going to be c, and then we're going to have gamma over 2 omega squared plus gamma squared, and then we're going to have, so right, that's plus, and then we're just going to have the same thing, right? So it's just going to be 2, which is going to cancel out. So eventually we settle on a position, right? And that's just basically, this is what happens when you grab the mass at the end of the spring and you just hold it there. It's a constant force, right? So eventually what happens is as the complementary solution dies off, then you settle at this position, right? This c times gamma over the quantity of omega squared plus gamma squared, right? So we kind of looked at three kind of, interesting cases of functions or forced oscillations or, forcing functions for the mass spring system. And that's basically going to do it for this video. So in the next video, we're going to look at part E, right? And something special happens if you choose this second case right here. So that's going to do it for this video. Thanks for watching, and I will see you in the next video.